Gnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we have been studying symmetric polynomials, and we have proved the fundamental theorem on symmetric polynomials, which says that every symmetric polynomial in n variables is a polynomial in elementary symmetric polynomials. This is very important theorem. This was proved essentially by Newton, and today I will discuss about the discriminants of a polynomial. So, in general, we have been dealing with discriminants of small degree polynomials in school and colleges, but today I will define discriminant for a general polynomial of any degree, and we will use it to study the Galois groups of some polynomials. So, as usual, K is our base field, and we have a general polynomial of degree n, that I have denoted Fn. This is a polynomial x minus x1, x minus xn, and we consider this as a polynomial over the rational function field in x1 to xn and x. This is what we consider this is a polynomial in x with coefficients in the rational functions. And we have seen that this polynomial has, when you expand it, it is x power n minus s1 x power n minus 1, etc., etc. Middle term is minus 1 power r s r x power n minus r, and the last term is 1 minus 1 power n Sn, where this S1 to Sn are elementary symmetric polynomials. And for safety, I will define S0 equal to 1. So, I have this, this is the general polynomial of degree n. So, when I have a polynomial in one variable over some field, then I will specify the this capital Xi equal to the roots of that polynomial and get back the original polynomial. That is that. Now, I consider this. So, let V, which is V of x1 to xn. You will see why I have chosen the name V. This is precisely Vandermonde's determinant. I will write here Vandermonde's determinant. And what is that? That is, you take the matrix xj power I is varying from 0 to n minus 1, and j is varying from 1 to n. So, it is to get our hands. So, for example, the first column is j is 1, right, and I is varying. So, 1 x1 x1 square, etc., etc. It goes down to x1 power n minus 1. This is the first column. The jth column will be 1 xj xj square, etc., xj n minus 1 and so on. This is a big matrix, it is n cross n matrix, and therefore determinant of that makes sense. This determinant is, you would have studied well in the college days. This determinant is, I am denoting by v. So, it is a polynomial in the variables x1 to xn. Okay. When you solve this determinant, you would have realized this is the value of this determinant is product is running over the indices 1 less equal to I strictly less than j less equal to n, and the product xj minus xi. I will just indicate how it is solved. You just subtract the column 1 from column 2, let us say, and then you take out the common factor x2 minus x1 and so on, and that is what you do it. So, this I would simply say this equality you verify. That is not too difficult. So, this is the Vandermonde determinant, and this is called Vandermonde determinant of x1 to xn. And remember, it is a polynomial over a field k. You can take any field x1 to xn. It is a polynomial there. Also, therefore, you can think it is a rational function. Okay, and the first important observation now I want to make in the following lemma. So, lemma: for every permutation sigma in Sn, if I permute a variable in the Vandermonde determinant according to sigma, that means I am taking sigma of this. So, this was the by definition what? This was by definition V of permute the variables according to sigma. This is x sigma 1, x sigma n. Now, if it is equal to V, then V will be symmetric. That was the definition of a symmetric polynomial, right? But this is not symmetric. So, this what comes out is sine sigma times V x1 to xn. Where sine of sigma denotes the signature of the permutation sigma. Now, I should digress little bit on the definition and some easy properties of the signature. That I do it before I prove this lemma, and then we will come back to the proof of this lemma. So, this says that this Vandermonde determinant is not a symmetric polynomial, but it is almost like a symmetric polynomial. Okay, so before we go on, now this is digression on the group Sn essentially. So, the elements are the permutations we know. So, sigma any element. Now, note that the sigma is a permutation. So, therefore, the sigma operates on the set 1 to n. So, therefore, I can talk about orbits. So, when I say orbit of O sigma 1, what does this mean? This means it should orbit of 1 under sigma. That means it starts with 1. Then let us go to sigma 1. If it is different from 1, stop it. Then if it is, then go to sigma square 1 and so on. Now you will come back to the power sigma power k minus 1, 1, and then I have chosen in such a way that these elements are distinct. Then you note that if I look at sigma k at 1, it has to be equal to 1, it has to return to 1. So, pictorially it starts like this. 1, you start with 1, then sigma 1, then go to sigma 2, then go to sigma 3, and keep doing this. Ultimately, you will come back to 1. This is sigma power k, 1, that will be 1. And just one before. So, why is that? Why does it come back to 1? Because if it does not come back to 1, then it will be some smaller power of sigma, but sigma has a inverse. So, just cancelling that, you will get a contradiction to the fact that these elements are distinct. Therefore, sigma power 1 is 1. So, this is called an orbit of 1. Now, you choose an element outside this and do the same process. So, therefore, what it means is, and if I restrict sigma to this set, so sigma restricted to, so I will write on the next page, sigma if I restrict to the orbit of 1, it is a very nice, it is actually what is a k cycle. What does that mean? That means we can write this as only elements which are disturbed under this is 1, start with 1, then it goes to sigma 1 and so on, it goes to sigma k minus 1, 1, and then it comes back to 1. So, you can complete it here. So, therefore, to this subset, if I restrict sigma, then it is a k cycle. The remaining elements under these are fixed. So, I can do now if 1 to sigma k minus 1 is exhausted all the letters, I keep quiet. Otherwise, I choose an element outside this and do the same thing. That means, this means if I continue like this means sigma is a product of disjoint cycles. I have defined what is a cycle. So, that means I have written sigma as a product of disjoint, that means they do not have anybody in common. This I have written it as some rho 1 etc., rho r, where rho 1 to rho r are cycles, and this may have length L1, Lr. That means this is L1 cycle, this is Lr cycle, and some of them could be 1 cycles. 1 cycles means they correspond to the fixed points. So, 1 cycles they correspond to the fixed points of sigma. So, if one wants to understand a permutation, one has to understand each cycles carefully, and they do not meddle with each other because they are disjoint, therefore, they commute. So, disjoint will mean that they commute. So, cycles disjoint, and that means they commute. Rho I, rho j will be equal to rho j, rho I. So, as far as finding the order of the permutation sigma in the permutation group, if we know the orders of these guys, then we will know order of the sigma, because they commute, therefore, the order of the product will be the LCM. So, the advantage is our calculation becomes easier, comfortable. So, from this we will know that order of sigma will be equal to LCM of orders of sigma, rho 1 to order of rho r, and therefore, we only have to know what is the order of a cycle. So, if you take a k cycle, that means what it is like this. In general, it is A0, A1, A k minus 1. It has k minus 1 elements in that. These are the elements which are moved under this k cycle. Remaining elements which are not here, they are fixed. So, the order will be precisely order of this, if you call this k cycle as rho, then order of rho will be nothing but k. That means rho power k is identity. That is easy, because once rho square will map, rho maps A0 to A1, rho square will map A0 to A2, and so on. When you take k times composition of rho with itself, you get back identity. So, for example, order of, if you take 2 cycle is also called a transposition. The transposition looks like A, B. There are only 2 elements which move under the transposition, A and B. Remaining elements are fixed. So, this is usually denoted by tau. So, tau square, if I want to compute, look at tau square of A, tau of A, this is tau of A, but tau of A is B, so this is tau B, but tau B goes back to A, so it is A. Similarly, tau square of B is B, therefore A and B are fixed and the remaining are already fixed, therefore we conclude that tau square is identity. And if A when one writes a transposition, then usually A is not equal to B, otherwise it is identity. So, therefore, order of a 2 cycle is, order of tau is 2. So, if you go on, then it is clear that order of a k cycle is k, and therefore, if you would have written sigma as a product of disjoint cycles, rho 1 to rho r, these rho i's are k cycles of disjoint. Disjoint is very important. Then the order of sigma is order of this product. Order of the product element in the group is not so easy to compute in general, but when they are commuting, then that order is nothing but LCM of orders of those elements. So, this is easy to check. So, one more, what is a 3 cycle? 3 cycle is, looks like this, A, B, C. That means A, B, C are moving, and this notation means A goes to B, B goes to C. So, if this is rho, this is 3 cycle. So, order of this 3 cycle will be 3. That is in general. So, we can easily compute. If I give you the permutation, I first decompose that permutation into disjoint cycles and read the order. Now, what is a signature? So, I would have to define signature in the same way. So, and also I should have mentioned earlier, 1 cycles are identity. 1 cycles are identity. Okay, so to define a signature, of permutation sigma, what is it? You first decompose into disjoint cycles, rho 1 to rho r, rho I cycles, and they are disjoint. So, therefore, support, what is support of a cycle? Support of any cycle rho is precisely the elements which it moves, that means the elements which it contains. So, if rho is this A0 to AK minus 1, this is a k cycle, the support of rho is precisely this subset A0 to AK minus 1. So, if rho is a k cycle, then the support of rho has cardinality precisely, cardinality of the support is precisely k. So, the support is a subset of 1 to n. And if you take their unions of the support, so if sigma is this written as a product of disjoint cycles, then we know that this set 1 to n is precisely the disjoint union of supports of rho I. I is from 1 to r. Disjoint union because they are disjoint, and therefore we have decomposed this set into this. Now some supports may have only the singleton, the one cycles are precisely the identity element. So they are one cycles which corresponds to the fixed points. So note that when you write one cycle simply means like this, but this is equivalent to saying A goes to A. So this is like identity. So when we do this calculation, we might as well assume that sigma is rho 1 to rho r, and they are cycles disjoint of course of length bigger equal to 2, because that is not playing a role, any role here. So those are precisely the fixed points. So therefore, to define a sign of sigma, I want to define sign of cycle first, where rho is k cycle. And this I define it to be equal to minus 1 power k minus 1. The number of elements minus 1. So this will give us sign of tau, where tau is a transposition, A not equal to B, then this sign is minus 1 power 2 minus 1. This is, so it's minus 1. So sign of a transposition is minus 1, sign of a k cycle is minus 1 power k minus 1, and then you define sign of sigma to be the product of the signs. This you define this. This is a definition. So that is the signature of a permutation. Now, what is the sign of a 3 cycle? Sign of say permutation 1, 2, 3. This means 1 goes to 2, 2 goes to 3, and 3 goes back to 1, and remaining guys are fixed. So this is therefore it's a 3 cycle. Therefore sign is minus 1 power 2, which is 1. So the permutations we have, which we have sign is therefore we have defined in a map. This is a map from the group Sn to the 2 element set plus minus 1. So any sigma goes to sin sigma. And what is more important is every cycle you can write it as a product of transpositions, for example. So for example, if I have cycle 1, 2, 3, this is a product of 1 goes to 2 composed with 1 goes to 3. Is clear? So one has to be little careful. How do you calculate? So first you go from right to left, that is like a composition, no? So here 1 goes to 2, 2 is fixed, so 1 goes to 2. I am checking this equality. 1 goes to 2, 2 is fixed, so 1 goes to 2. Where do 2 go? 2 goes to 1, then 1 goes to 3, so 2 goes to 3. Where do 3? 3 is fixed under this, and 3 goes to 1, so this 3 goes to 1. So that is how one decompose cycle into product of transposition. But remember, these are transpositions, but not disjoint. They are not disjoint. So similarly, you can decompose any k cycle into product of transpositions. And this way we would have decomposed any sigma in Sn is a product of transpositions. But we cannot say now the product of these transpositions is disjoint, that we cannot say, may not be disjoint. But what we can assert is the following easy lemma, which I am not going to prove, and I will leave it as an exercise. So, if sigma is a product of disjoint transpositions in two ways, tau 1 to tau r and tau 1 prime to tau prime s, where tau I, tau prime j are transpositions, then these r and s, they are equal mod 2. This is easy verification, which I am not going to do, but this will allow us, therefore, once important consequence will be, corollary will be the sign map from Sn to plus minus set. Now, this is a group under multiplication, this is also group under composition, and this map is a group homomorphism. So, signature is a map, and therefore, kernel makes sense. Kernel of sign. This, and obviously this group homomorphism is non-trivial. Non-trivial means when n is at least 2. Non-trivial means everybody does not go to 1, at least one element here goes to 1, well, but the transpositions are going to minus 1. And because n is at least 2, there are transpositions. And therefore, kernel of this homomorphism is not the whole group, it is properly contained in Sn, and these are precisely all those permutations sigma such that sign of that sigma is 1, and sign is 1 means the sigma is a product of even number of transpositions, and therefore, this group is very important, and that group is called, so kernel of sign, this is the definition, this is An, this is a subgroup of Sn, and this is precisely all those permutations sigma in Sn such that sign of sigma is 1, but this is same as all those permutations sigma in Sn such that sigma is a product of even number of transpositions, and it is also clear that this is An is normal subgroup of Sn, because it is kernel of a group homomorphism and of index 2. In fact, it is very easy to see that this group Sn is same thing as An disjoint union any transposition times An, where tau is any transposition. That is very clear because we know that this An is a kernel, therefore, what we know is Sn modulo the kernel, that is An, this group is isomorphic to the group plus minus 1. This group has cardinality 2, therefore, this quotient set has cardinality 2, that is the meaning that it is index 2, and therefore, this decomposition, there are only two cosets of an in Sn, and they are precisely this. With this, I will prove the lemma in a next half, and we will continue after this digression of a group to study. I have not yet come to the definition of a discriminant. So, I will study the Vandermonde determinant under we want to check that if I permute the variables in the Vandermonde determinant, what happens to that determinant is it changes the sign according to the permutation sign of that permutation. So, I will continue after the break.